Welcome back to calculus. We're going to look more at volume. How do you find volume of a solid rotated around a axis? In this particular instance, we're actually going to be doing a vertical axis. Well, maybe I shouldn't have told you that. Maybe we should have just figured that out as we went. Now, I wanted to go through a couple of different types of methodologies in some of these videos to kind of give you different ways to work these problems out. So what I'm doing in this one is I actually went just to a cloud-based graphing calculator system, and I just graphed the equations out. And in fact, the particular one I was using, I could have graphed out x greater than or equal to 0 as well, and including x minus 1 as my axis of rotation, and had all that on one graph. But I thought this was plenty good enough to get all of the pieces, and I have a minimalist approach to it a lot of times with these things. Now, if I were to graph this and I rotate this, I'm going to be rotating around the line x equals 1, which is right here. And I always use a dashed line for that. So that's, put a little arrow, a little circle like that around it. So this is x equals 1, negative 1 actually, pardon me. And that's my axis of rotation. So when I rotate around this axis of rotation, what is the figure I get? Well, we first have to identify what is the region we're dealing with. So f of x is equal to 3x, which is this red line right here, this straight line that starts at the origin and goes up and over as an increasing function. And then we have g of x, which is negative x squared plus 5, which is a parabola opening downward with a y-intercept at 5. And then is decreasing on the right-hand side, which is the piece that we're concerned with. Now, this is the interesting piece of this, is that the left-hand side of this curve, the left-hand side of this parabola, is not of use to us. Let me see if I can get, there I can get wide, right? So I can get rid of that piece of the curve right there entirely, maybe not entirely, but I can just get rid of it because I don't need it. Okay, so if you're doing this on paper and pencil, you can just literally just erase that part of the curve because we don't need it anymore. Okay, so that's what I need. Now, when I rotate this, what does this shape look like? Well, if I go over one unit here, this grid is actually broken up in terms of halves. And then I can kind of recreate this more or less just over 2 units that way, right about there. And then it's going to go through directly below it right there. So there's a straight line here, and then there's curved line here, and then I have this flat piece right here, right? So that's what I'm dealing with, is that little shape right there. So I don't really have a good explanation. There's a cylinder in the middle of this thing, and it's kind of straight on one end and curved at the other, so I'm not really sure what that shape would kind of look like. I don't know if I can draw that very well. Maybe a little bit like this. So maybe a little bit like a vase, right? Because it had kind of curved bottom, but it's got this cylinder running through it, right? That's a horrible drawing. You can pretend. All right, so that's kind of what we're dealing with over there. So get that out of the way. We don't want to look at that. Okay, so now what? We got the basic shape. And the shape, I think, is less important than the actual process that we're going through. So what we need, once again, is we need to pay attention to the fact that we want to go from here to there, right? We want to figure out what that piece is. That axis rotation is the distance from the axis to the outside edge is what we're wanting to deal with. Now, what's interesting is in this one is it actually, we have this point right here where we switch. So if we were to go from here to here, we actually have, in this instance, big R1 and big R2. We have 2 different outside radii because the figure changes which piece is defining that outside edge. Okay? And then from here to here is that inside edge of our axis of rotation. In this case, this is little r, and it's actually the same all the way around. Okay, so that's set up pretty nicely here. So we're going to do the integration. We're going to have a pi here. We're doing a rotation, and when we do that cross-sectional cut, we're going to be dealing with a cut that is still a circle. So that's going to be good for us to identify because now we know we're dealing with something squared minus something squared again, right? And then d something. Now, we'll deal with the fact we have 2 big R's here in a second. First, let's deal with what is the something here, d what? So as we think about this, if we think about stacking, these are slices of bread, of a weird-looking loaf of bread here, and we start stacking these slices of bread up, we're stacking them horizontally. We're creating a tower. off the counter as opposed to building a tunnel on the counter or whatever you want to visualize that as, right? We're building a tower. So if we're building a tower here, we're going up. So if we're counting in terms of y, the y values are what's going to change. Each slice is going to have a different y value as we build up that way. Now you may be thinking, well, we're going to have a different x value too. Well, yeah, that's true, except this y value and this y value and this y value all have the exact same x. This y value right here, if you're looking at the in this first quadrant here where R1 is on the right where it touches the parabola, that x value corresponds to another x value right here on the red line. They have the exact same x value. So you actually are, what's changing here are the y values more than the x value. That's what's going to determine what's really controlling the stacking process of this particular shape. I hope that helps a little bit. So now we know we need to go from y equal to something to y equal to something. So we're going from y equal to 0, there's the easy part, to y equal to 5? Well, here's the problem. Okay, so this is up here is actually 5 because we have at negative x squared plus 5. So this top piece right here, this value is 5. But we switch from this blue curve to this red line here at some point, at this point right here. So we actually need to account for that. So we're actually going to do a whole nother one. So we're going to go up to something. We don't know what this is, but luckily it's the same for both of them. We're going to go from 0 to something, and then we're going to go from something to 5. And we're going to go something squared minus something squared, and it's still luckily going to be dy. So if all we got to do is just figure out R1, big R2, and little r, and then we need to figure out what that something is, and we're set with this. Okay, so let's first figure out our r's. So let's figure out R1, let's figure out R2, and let's figure out little r. Okay, so R1 is the distance from the axis of rotation over to that outside edge. Now, if you think of this, think this through for a second, we're dealing with the fact that this right here is a length of 1 from the axis of rotation to the y-axis. That's a distance of 1. And then from there to the outside edge is some distance of x. Okay, we'll call it x sub 1 right now to correspond with it being R1. So that means that in this instance, what we're actually doing is we're doing 1 plus x sub 1, all right? So, but remember, our equation has to be in terms of y because we've already defined this to be dy. So x1 in this instance corresponds to that parabola. So this is 1 plus negative x squared plus 5, which means that R1 is equal to negative x squared plus 6. Now, that happens to be the upper section of this shape here, this solid, which means that this is going from something up to 5. So there's negative x squared plus 6. All right. So let's then figure out little r because let's just finish out this little piece here. So little r is the distance from the axis of rotation to the inside edge, which in this case is just the y-axis. And that's a distance of 1. It's a constant. Well, that was nice, right? So 1 squared. So that's going to be the same up here for the first part of this one, right? Keep in mind that we're going to be adding these two together when we're done, okay? And that's going to give us a total volume for the two of these things, right? Whatever that is. So this is going to give us volume 1. This is going to give us volume 2. And volume 1 plus volume 2 is going to give us our total volume for these two pieces of this object here. Now let's figure out R2. R2, once again, luckily it has that same distance from axis of rotation to the x-axis, and then we have this distance x sub 2 from the axis to the red line there. So what we got there is 1 plus x sub 2, all right? So in this instance, x sub 2 is defined by 3x. So this is 1 plus 3x. So there is my other piece of that, 1 plus 3x. Now, the only thing left to do is to figure out what this something is. I have these question marks I got to replace, but it's the exact same spot. So once I find one question mark, I found both question marks. So how do I do that? Well, what I need to do is figure out where these two equations intersect each other. So that's going to do 3x is going to be equal to negative x squared plus 5. All right, so I'm just going to move everything to the left-hand side of this equation, which means I end up with x squared plus 3x minus 5 equals 0. Now, if you remember your factoring, we're trying to think of something that multiplies to negative 5 and adds to positive 3. Well, the only thing you got for 5 is negative 1 and 5, and negative 5 and 1. Neither of those give you 3, so this does not factor nicely. So our go-to method then is our quadratic formula, which is negative b. All right, here are my a, b, and c. So my a value is an understood 1 right there, right? So negative b plus or minus the square root of b squared minus 4ac all over 2a. All right? Now, I forgot my negative right here with the 5. There we go. Put that in there. Okay? So we get x is equal to negative 3 plus or minus. This is 9 minus, or x is actually 9 plus 29. So this is 29 here. Okay? And that's all over 2. Okay, so in this instance, we actually want a number, a value of some sort that we can work with. We can leave it as an exact value until we actually plug it in, but for our sake in this instance, I'm actually going to go ahead and figure out both those values. So we'd have negative 3 plus the square root of 29, and then divided by 2, which gives us 1.1925, and it keeps going on forever. All right, now when we do the other version of that, so that's negative 3 minus the square root of 29, that's going to give us a negative value, which doesn't make sense in this instance because we already know the x value has to be positive, so it's actually going to end up being some negative quantity of some sort because it would occur way down here in the graph, like our parabola would. Our normal parabola, if we remember, we erase that line, it keeps on going down and down, and then our red line goes down. So there's some type of intersection point way down here that is x equal to some negative quantity, which we don't want to use, right? So what we're going to use here, oops, I erased too much. All right, so we got the integration from 0 to 1.1925 and 1.1925. And you can take that as far as you can. The more you take it out, the more accurate you're going to be, but that was a pretty messy quantity right there to use to plug in. But if you wanted to plug in the exact value, you just would have plugged in negative 3 plus the square root of 29 over 2 right there where we have that piece. Now on your calculator, I know on the 84 and the Casios, you can actually store a quantity like this into a variable and then actually use that quantity, that variable as a constant on your calculator instead of typing that out. And that does give you the exact value. So at this point, it's just the two polynomials that we would need to multiply everything out and then do integration with first, and use your first fundamental theorem of calculus to find these two independent volumes, add the volumes together, and you have the total volume units cubed, or whatever the units here. If they said this was inches, and this would be inches squared, or whatever it would be. All right, so I hope this example was useful and helpful, and if you need more, please reach out and ask. Otherwise, have a great day and take care.